Now, let's think about board games. Let's go from solitaire puzzles to board games. What does it mean to have a winning strategy in a game? So on the left here is a classic chess puzzle by the famous among people who love puzzles, puzzle designer Sam Lloyd. I am actually pretty bad at chess puzzles, but this one says that if you're clever enough, you can achieve checkmate in 3 moves. On the right, you see another chess puzzle made with the aid of a computer, that there is a checkmate available in 262 moves. Solving this chess puzzle is probably beyond the abilities of human beings, as well as beyond our interest. But what does it mean to have a winning strategy in a game? Well, if it's my move, it means there exists a move for me such that no matter what you do next, for all of your moves, there exists something I can do, so that no matter what you do after that, there exists something I can do such that, etc., until I win. Now, when you think about it, this is a complicated, nested series of these logical relationships. It isn't just a single thing that exists. It's not enough just to tell me what move I should do first. You have to tell me what I should do, how I should respond to all possible lines of play. And there is, of course, a huge tree of where the game could go, depending on what moves you and I make. So the long and short of it is, if I want to prove to you that white has a winning strategy in chess, or let's say generalized n-by-n chess, it's not clear how to hand you a proof that you can check, because the proof itself is an enormous object, an exponentially large table of what you should do in every situation. And this tells you that strategies are larger things than, say, Hamiltonian paths or colorings of a graph. And in fact, for this reason, playing games perfectly lives higher up in the complexity hierarchy. So if we have a game tree of all the possible directions that a game could go, let's say we're playing tic-tac-toe. So here is this game tree. Again, the root is at the top. That's, say, our current position. And then depending on whose move it is and what they do, we go down to various children and grandchildren and so on, until at the end, either X has won or O has won, or it's a draw. Now, exploring this entire tree could take exponential time. But there's a nice fact about it. In games like tic-tac-toe, the board gets filled up. So if I have a board with n places to play on it, we know that the game will last at most n moves. That means the depth of this tree is at most n. Because of that, it turns out that we can explore this entire tree using a technique called depth-first search. It might take exponential time, but the amount of memory we need is only proportional to the depth. So for many games, we can play them perfectly, we can play them optimally, figuring out who is a winning strategy and if so, how to achieve it, with a polynomial amount of memory. Remember, we talked before about how, yes, we're usually concerned with running time, but memory matters too. So there is another complexity class above NP called PSPACE. We could have called it P-memory, but we call it PSPACE. It means the set of problems which can be solved with a polynomial amount of memory, even if they take exponential time. I want you to think, why is NP contained in P-space? All you need to do is choose your favorite NP-complete problem and confirm that we can solve it using a polynomial amount of memory, even if it takes you exponential time.